Welcome to this lecture series in number theory. In today's lecture, we'll discuss Bezout's theorem, and then in the next lecture, we'll look at some applications of it. Before we get started, I just want to prime you with these two snippets, which we have discussed earlier. This is a simple fact about GCDs, and this is the division with remainder theorem. All right. Some problems for practice. And now let us get started. So, before we state and prove Bezout's theorem, I want to discuss an interesting but simple lemma, which will be instrumental. So, fix a subset of integers as we say that it is closed under addition if, you can guess, if for all x and y in the subset S, or maybe I'll write it this way, whenever we choose x and y in S, we get that their sum is also in S. Very simple definition. It is closed under addition, right? If you pick two elements and add them, they remain there. So it's a natural definition. And an example would be, you take the set of natural numbers. This is a set which is closed under addition, or you can take tails. So suppose I take this, k is any natural number, then this set which is defined as follows, all those natural numbers which are at least k. So those are also closed under addition. If you add two natural numbers, two elements from here, they will remain here. They will not pop outside. And you can construct many examples, like you take set of all the even integers. That is also closed under addition because sum of two even numbers is again an even number. The set of all the odd numbers is not closed under addition. If you add two odd numbers, you do not get an odd number. It is highly non-closed under addition. So it's a simple concept. I don't want to waste too much time on it. Another related concept, fix a subset of integers, call it S. We say that S is closed under additive inverses if whenever we pick x in S, we find that its additive inverse remains in S. So this is also a very simple concept. Examples, well, I do not want to give any concrete examples, but there is essentially just one way to build them. You first pick any subset of natural numbers, or if you want, you can pick a subset of whole numbers. Then what you do is you construct its ghost copy, meaning construct the set of all the additive inverses of it, and then take the union of these two things. That's precisely, those are precisely the subsets which are closed under additive inverses. I think that should be clear. So here I don't want to write anything. Right, so these are two special kinds of subsets of integers, and there is very little mystery to them. But something interesting happens if you have a subset which satisfies both these closure properties. So fix a subset of integers. Assume it is closed under addition and also under additive inverses. Then this kind of subset is very special, and the theorem says that there is some non-negative integer n such that S is equal to nz, where what is nz? Recall, nz is nothing but all multiples of n. That's what nz means. So clearly, if you have a set like this, you pick any non-negative n, or in fact pick any integer n and construct nz, or consider nz, it will satisfy both these properties. If you add two multiples of n, it is again a multiple of n. If you take the additive inverse of a multiple of n, it is again a multiple of n. So these sets do satisfy both these properties. The point of the theorem is that the converse also holds. Okay, so that's what we want to prove, and I in fact encourage you to pause the video and try to prove this yourself. right? It's not a hard statement, but it has something to teach us. So here is a proof. So if S is the set 0, if S is this set, then we are done, right? This set is, of course, both closed under addition and additive inverses. And if this were our set, then you can just choose n as 0 and that validates the proposition. So we want to prove it in the case when S is not this triviality. So assume S is not this set. Okay. Note that S contains natural numbers. Why is that? Well, pick any non-zero element in S. Since S is not this trivial set 0 or this singleton, it must contain something non-zero. You pick anything non-zero in S. If it is already positive, then this statement is, this remark holds. If it is not positive, then it is negative. And then you can use this property, the second property, to take the additive inverse of it and therefore find a natural number in S. Right, so this is a simple check. Now we take, I don't want to use n, but anyway, so let n be the smallest natural number in S. Okay, so we pick n as the smallest natural number in S. Since S has some natural numbers in it, it is we just showed that it has at least one natural number in it. So this set is non-empty, and therefore it has a minimum. Any subset of natural numbers, any non-empty subset of natural numbers has a smallest element. That is called the well-ordering principle. Okay, so this is a well-defined natural number. All right. It's a triviality. The statement is at least intuitively trivial that every non-empty subset of natural numbers has a smallest element. But whatever, that's a very crucial statement in mathematics. So you pick that, and now we claim that S is equal to nz. So first note that this containment holds. Once n is there in S, nz is definitely there in S, contained in S, right? N is in S, and now since S is closed under addition, n plus n, which is 2n, this is also there in S. Then you further add n to it, you get 3n is in S. So all positive multiples of n are in S. Similarly, since S is closed under additive inverses, we see that minus n and by the same token minus 2n, minus 3n, all of these are in S. And now since n and minus n are both in S, their sum is also there in S because S is closed under addition. So 0 is also in S. So this containment is obvious or requires a little bit of an argument. So I'll just write it. Clearly, this containment holds. Right, I think I garbled my speech a little too much there. Basically, once you have n in S, any positive integer multiple of n is also there in S. That is easy to see because n plus n, n plus n plus n, n plus n plus n plus n, all of those will be there in S because S is closed under addition. And now if you use this property further, you just play a little bit, you will get this containment. We want to prove the reverse containment, which means to prove what? Which means to say that everything in S is divisible by n, right? So that's what we want to do. So pick x in S arbitrarily. We want to show that n divides x. Once we do this, we will have proven the claim and the theorem or the lemma. So why is that? Well, what do you do when you want to say that something is divisible by something? You use the division with remainder theorem. So say x is equal to nq plus r, where q is some integer but r is in this range. right? Now, if r is 0, then we are done, because then n will divide x. So assume r is positive. So assume r is positive. Then what happens? Then r, or rather, I mean, I didn't want to write a then, but if r is greater than equal to 1, then we are arguing that, note that r is x minus n cube, which I'll write like this, x minus qn. And now note, x is in S, minus n is also in S, so I'll write it like this. I'll write it as, for the moment, think of this as a positive integer. It's not necessary, but just think of it that way. So write r as this, and now since n is in S, minus n is also in S, because S is closed under additive inverses. Therefore, this is also in S, right? Any multiple of whatever is there in S has to be in S. In fact, we already showed that nz is contained in S. So this is in S. This was anyway in S. This we picked in S. So their sum is also in S, right? S is closed under addition. Therefore, r is in S. But then r would be a natural number, smaller than n, but also in S. However, n was the smallest possible natural number that was there in S. This reasoning, if r is at least 1, would show that there is an even smaller natural number that is there in S. And that's a contradiction. So r must be 0. If r is positive, we get a contradiction. So I hope this reasoning is clear. I have said it in words. I haven't written the full thing. Said a lot of things in words. But I hope you follow. And it is important to digest this lemma. It should be crystal clear. Okay, and now we can go to proving and stating and proving Bezout's theorem. So first we will prove a special case, which is really the main case. So suppose A and B are relatively prime, which is to say that their GCD is 1. Alright. What do we want to show? We want to show that there exist integers x and y such that this equation holds. Okay, and the converse is also true in the sense that if this equation holds for some x and y, then GCD of A and B is 1. That I leave as an exercise. You take the GCD of A and B, you notice that it is dividing the LHS. Okay, whatever. So we are going to focus on this part. That's the difficult part or whatever. It's non-trivial. And here is the proof. Well, if you followed the previous module, which was in a sense optional, then you already see why this is true. But we will give an independent proof of it. And as we promised, we will then also talk about inverses. I mean, this is basically a theorem about inverses, if you look at it. We will make all the connections formal. But yeah, so we are going to give basically an alternate proof of the existence of inverses. And it's a very, very neat piece of reasoning. So what do we want to do? We want to prove the existence of such x and y. Such x and y meaning such x and y. And the first step of the proof is already very beautiful. So it says that collect all those numbers that you can form in this fashion. All those integers that can be formed this way, collect them in a set, and then we want to prove that 1 is there in that set. That's kind of a global perspective. That's a very modern way of looking at things. So define the set S as all the numbers that are of this form, where x and y are integers. And I could have written this set as follows. That's a very nice way of writing the same thing. Anyway, that's just a notation for this. Okay, so this is a set, and here is the main observation. Note that S is closed under addition and additive inverses. Simple observation, but crucial. closed-ended addition, because if you add two things of this sort, you of course get something of this sort. And same for additive inverses. So it's a very simple, very easy to verify observation. And also further note that A, B, minus A and minus B are in S. Right? If you want to prove that A is in S, just take X as 1 and Y as 0. And similarly for the others. So this is there, and since A and B are not both 0, they are relatively prime, so they are not both 0, we see that S is not the triviality. S is not the singleton. Right? Because at least one of A or B is non-zero. Alright, great. And now by the previous theorem, there exists some positive integer D such that the set S is dz, which again I'll recall what is dz. Dz is all multiples of D. Okay? So we have that, and our claim is D is 1. In fact, the way we will prove it is that D divides A and D divides B. Right? This is what we will do. Once we do this, then D is a common divisor, in fact a positive common divisor of A and B. And then the relative primality of A and B will force that D is equal to 1. So I'll just mention it here, which will imply that D is 1. And that will finish the proof. As soon as you show D is 1, we see that 1 lies in S. And that's all we wanted to do. So here I'll also make that note. Want to show that 1 lies in S. That's precisely what the theorem says. Okay? This is what we wanted to do. And once we do this, we will be done. That much should be clear. And now let's get to proving this. So we will just need to prove that D divides A. Once we prove that D divides A, the other part is very similar. I mean, it's basically the same thing. And again, how do you show that something divides something? You use the division with remainder theorem. So say A is equal to dq plus R, where R is in this range. And once more, if R is 0, then we are done. So may assume or just assume R is at least 1, and we want to bring a contradiction. Right? Once we bring this contradiction, the proof will be over. So R is at least 1, and now note that since R is A minus dq, we see R is in S. Right? A is in S, D is in S, hence dq is in S, hence A minus dq is in S. S has the two properties, closed-ended addition and additive inverses, shows that this is there in S. So R is in S. Okay? But if R is in S, then D divides R. Right? What is S? S is precisely those things which are divisible by D. If R is in S, then D divides R. And that forces that R cannot be at least 1. So in fact, we didn't really need to go by contradiction. We could have erased this and just wrote this piece of reasoning here. Better to not go by contradiction when you can avoid it. So we just notice that R is A minus dq, and therefore R is in S, and therefore D divides R, because S is precisely the things which are divisible by D. Now the fact that R is in this range implies that R is 0. I mean, in fact, yeah, so it implies that R is 0. And that's it. That's what we wanted to do. Once R is 0, D divides A, and we are done. Because once we show that D divides A, we similarly show that D divides B by precisely the same reasoning, and that, as we said, implies D is equal to 1, and that proves this theorem, which is a special case of Bezout's theorem. Okay, so it's a very short proof. If you think about it, all it is saying is that there is an inverse of A modulo B. This statement is saying exactly that there is an inverse of A modulo B. If you remember the definition of inverses, we will recall that definition today. And also recall the length of the proof that we gave and the complexity of the proof that we gave earlier. Okay? Here it's very short, like less than a page. If you combine the previous and this page and type it out, it will be less than a page. Okay. Now for the general case of Bezout's theorem, fix two integers a and b, again not both 0, and let's say d is their GCD. Then we want to say that there exist integers x and y such that ax plus by is equal to d. So d can be written as an integer linear combination of a and b. That's how you say it sometimes. And the proof is very simple. Proof is that GCD of a and b, or rather I'll say GCD of a by d and b by d is 1. This we recalled in the beginning also. This is something that we proved in the previous lecture, and if you have forgotten, you can just spend a few minutes and prove it again for yourself. And that is the best way to learn these things. And now use the special case of Bezout's theorem. So this implies that there exist integers x and y. By the special case of Bezout's theorem, there exist integers x and y such that a by dx plus b by dy is equal to 1, and that's it. Cross multiply, you get this thing. So the GCD of two integers can be written as an integer linear combination of the two integers. And everything that can be written as the integer linear combination of two integers will be divisible by d. So here is a better statement that we could have made than the one that we have made. The better statement is az plus bz is equal to dz. Where recall az plus bz is the set of all such numbers, right? So by this thing, you can imply or easily prove this thing. I leave that to you, because anything of this sort is divisible by d. So this containment was anyway obvious. The other containment is proved by this theorem. Okay, wonderful. And now let's talk about inverses, and that will be it. So let's recall the definition. Suppose we have a non-zero integer n and some integer a. We say that u is an inverse of a modulo n if this congruence holds, if a times u is congruent to 1 modulo n. That's the definition of inverse. You've seen it before. And here is the thing. Suppose, again, n is a non-zero integer, a is some arbitrary integer, then the following two things are equivalent, which are that one point is that a has an inverse modulo n, meaning there exists such a u, and the other is that a and n are relatively prime. And this is just an immediate consequence of Bezout's theorem. If a has an inverse modulo n, then a and n are relatively prime. That should be clear to you by now. Because if a has an inverse modulo n, then au is equal to 1 plus nv for some integer v, right? That's what this congruence means, which means au minus nv is equal to 1, which means what? You take the GCD of a and n, it divides the left-hand side, and hence it divides 1, and hence any common divisor of a and n, and hence the GCD of a and n divides 1, which means the GCD is 1. So that reasoning we have done many times, and that's clear. The other direction is the difficult direction, but that is immediate from Bezout's theorem. So we will just talk about this, and there is not much to write. By Bezout's theorem, there exist integers x and y such that, or I'll write u and v, such that au plus nv equals to 1. That implies AU is congruent to 1 mod n, and that proves that U is an inverse of A modulo n, then we are done. So very, very simple discussion on inverses, nothing close to the 4 or 5 lectures we spent on it in the previous module. Still, why did I do it that way? I think the lessons that we learned from those or that approach are important, and they are not present in this proof. This proof is a pristine, polished proof. It is short, but it has little thing. I mean, compared to the previous proof, it has very little to teach us, and very little to give us a feel of what's going on. In the previous discussion, we drew so many pictures and kind of explored the structural aspect of things, whatever that means. Okay, so that's the end of today's discussion. In the next lecture, we will look at applications of Bezout's theorem. Very important facts about GCD, etc., and also look at many interesting illustrations and puzzles. All right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.